Hello, everyone. Welcome to this week's binary episode of the Day Zero podcast. I'm Spectre. With me is Z. As usual, I'll let Z get into the Spot the Vuln challenge here, which was quite a long one this week.
Yeah, definitely a longer one, a bit more context to it, but somewhat straightforward to at least understand what the core issue is. Some people did call out some other issues with this. I did copy this code out of the Art of Software Security Assessment, um, or largely, and then removed a little bit to make it a little bit more concise. The thing you kind of need to keep a lookout for is when you have these reallocated buffers going on. That's kind of the root of this. On line 6, you'll notice, or well, you've got the condition on line 5. If the buffer's been entirely used or would be, it'll reallocate a new larger buffer to hold the new data that you're appending into it. Um, so what can end up happening with that is when you use realloc, you're getting a new allocated buffer out of it. So if anything took a pointer to that buffer, that pointer can then become stale or dangling, just basically pointing to the no longer used memory, which is exactly what happens down in the process token string. Line 25, you have that toke start variable. It's getting a pointer using buffer data, and then it will still end up calling read data, which is supposed to be the read line function that ultimately calls buffer append. I forgot to fix that up before posting, but it'll call that, so that can potentially end up reallocating the buffer, leaving that dangling pointer, and then whatever process token does later on using that, will basically be using that dangling pointer. So a lot of code to get there, but nothing too crazy in terms of the actual issue.
Yeah, you just kind of have to look at the context surrounding it and what it's doing more closely than perhaps some of the other Spot the Vuln challenges we've done. So, uh,
Yeah, it's something
or
different. I wasn't
yeah, it's a
going for
little different.
integer overflow this time, although some people did call that out as a possibility. I left out the whole structure information for the data buffer, being within it's kind of a mystery what the size is and if it's practical to do it as an indicator of looking somewhere else for the issue. But that was still called out, and yeah, there isn't. There's perhaps the possibility of overflowing something here, in that sense, but odds are you're dealing with 64-bit sizes at least. Um, or just before the podcast when I was talking to Spectre about it, I joked about using GCC has their 128-bit int type that the compiler specifies, so you'd have to send a lot of data to overflow those integers.
I think you blow up your router first. So, yeah. But keeping on the topic of overflows, I guess we can jump into our first topic here, which is an out-of-bounds read in Chrome's PDFiumEngine, specifically this request thumbnail method that was detailed by Project Zero. The problem here is really quick. They use this page index parameter, which is passed as an int and used to index into this pages vector. If it fails to get a progressive index, so if the page isn't being progressively painted. And there they call a method on a pointer from that table for the request thumbnail callback, and that page index parameter isn't validated at all in production builds. So you can get an out of bounds read on that pages vector. They do have a dcheck like macro call, which calls page index in bounds, but since that's a debug check, it doesn't get compiled in on production build. So it's one of those bugs where um,
Yes, those
for
bugs.
whatever reason, they just decided that the check shouldn't be there on production builds.
I mean,
Um,
it definitely it would add some. I'm sure they'd gain some performance there. I don't know how often anything's really going to be calling the thumbnails that makes it really worth saving. Um, yeah, I mean, we've had this discussion over debug checks versus keeping them in, and mostly around asserts, but kind of the same deal here. So we probably don't want to get into that again, but I kind of lean towards going for less performance, and higher security. But I mean, it is a browser engine. They care a lot more about performance than I generally do with my very hacked together programs.
yeah, there is a performance sensitive context there. So there is a bit of reasoning as to why they might have the debug check only being a debug check, but in this case, it was erroneous to do so. I believe this should be a pretty easy code exec vector. Now, I this is an area in the browser I've never looked at, to be clear, so I'm just basing this off of this report in isolation, basically. But from what I'm seeing here, you can effectively get some out of bounds pointer to be read in as if it were a page, and then they invoke this callback on it, this request thumbnail callback. So it should be pretty easy to like get a pointer to point to data that you control, and then you can just control the method that gets called by doing like a fake v table or whatever. Like this seems like a one of the more straightforward bugs to exploit in the browser. So I found that kind of interesting with this. I don't think they really touch on the exploitation angle, which they usually don't in the Project Zero reports. It's just like here's the bug, here's like an ascend crash, and uh, get it fixed. But yeah, I'm pretty sure this could be exploited fairly easily, especially with the browser and how much control you have over the heap. So yeah, cool bug. And with that, we can move into our next topic, which is three detailed vulnerabilities in APC Smart Universal Power Supplies, which, according to Armis, is one of the leading providers for uninterruptible backup power supplies worldwide. They named these vulnerabilities TLStorm to kind of classify them all under one grouping. Um, Two of the three bugs are RCEs and TLS packet handling, which I think we'll start off with before going into the third bug. Um, the first of which is a state confusion with handling of the TLS handshake, which yields auth bypass, and the second is a buffer overflow. Both bugs were a result of improper use of the Nano SSL library, which APC used, and by that I mean they just ignored errors and return values in certain locations, or just didn't handle them correctly. So kind of a classic kind of issue to look for. Starting with the auth bypass, they looked at the TLS handshake process, and at a high level, what's happening with the library is a client attempts a connection. It's supposed to send this client hello message with session information, and the server is supposed to send back a server hello message with its session information and everything too. It gives you like a session ID and whatnot. And there's two important bits for the bug here. First, upon receiving a server hello message, it'll check the session information, and if it matches the TLS connection state that the client is maintaining, it'll just resume the existing session basically. If it doesn't match, it'll set the session ID and do validation, key exchange, and such. The second important bit is the server and the client have to agree on a cipher suite, or they both have to support the cipher suite that's being used. So they kind of investigated what happens if the server chooses a cipher suite that the client doesn't have support for. Well, it's supposed to fail and return an error. Um, but the problem is with the library here, because they're ignoring that error, they're ignoring the return value. The state of the TLS connection never gets updated. Normally, upon error return with this function, you're supposed to terminate the connection, but here it basically just ignores it and continues, which is a problem because a malicious user can then send a second hello message. It'll see the session information from the first failed message that's stale in the TLS state, and because the state was never like fully completed, a master secret was never generated for that connection because it wasn't fully established. So it's just left uninitialized at zero, which is obviously easy for an attacker to predict to finish the TLS resumption. So kind of this case of using an incomplete TLS connection state that allows auth bypass.
Yeah, and the key thing there, just to mention with auth bypass, is the auth that it's talking about is what usually happens at like the TLS layer. So that's the certificate validation of actually being like, hey, am I actually connecting to the server? I think. Um, so like for somebody to actually exploit this, they have to kind of be in that man in the middle position of being able to pretend to be that target server that the client is trying to connect to. So it is a little bit of an ask on that side, but given the type of device that's kind of also, I think, in the threat model for it, a more local or uh more localized attacker, I guess. But yeah, the authentication is kind of at that level, not like an application layer. Well, yeah, not further down. It's just the authentication of the TLS itself. So it kind of allows spoofing without actually having the proper certificate.
The second bug was in the packet reassembly for TLS records. Basically, what's happening there is TLS implementations over TCP will uh, try to send frames over TCP. So they have this 4-byte header, which contains the content type, the version, and the length of the payload or the packet, which is then used to parse the next length bytes of data as part of that content. Just a simple header followed by auxiliary data buffer. Fairly common to see in networking. And those fields aren't encrypted because this is all happening pre-auth. Now, since multiple things are being transmitted here, the library has to keep track of the reassembly state as it receives the records. So it'll set up this initial state of before header, receive the header, which then switches state to after header, which will then extract that length and try to copy the payload into the incoming message buffer. Um, What's kind of important to note there is if you pass a length that's greater than the current size of that incoming message buffer, it will usually try to reallocate if it needs a larger length. The problem is if you look at the decompilation code, which I believe is on page 19 of the white paper, you'll see that they have this maximum on the packet length, which is 2389 bytes. And if your packet length hits that value or exceeds it, it'll return this error code, like length limit violation error or something like that, and it won't reallocate that buffer. Again, just like with the last bug, a function higher up in the call stack, COAP receives sockcb in this case, doesn't check this return value, and thus if you pass this packet with a really large length, the old buffer gets used since it didn't get reallocated to accommodate the newer size, and overflow occurs there when they try to use that size. Since this is all being handled pre-auth, since the bug is into handling of the TLS headers themselves, this offers a pre-auth RCE vector as well. The final bug was a bit of a higher level issue and was mainly just the fact that symmetric encryption was used for firmware updates, and they didn't really have any proper code signing in place, like they didn't use RSA or something. So, because there's just symmetric encryption going on, um, and there's obviously no personalization of these firmware updates, by just pulling the symmetric key off one machine, you can use it to encrypt malicious firmware updates for other UPS, and there's no secure code signing in place. There's no validation that that firmware actually came from the vendor. Um,
Yeah, and I mean, I feel like we've half covered that issue quite a few times over on these binary ones,
it's a
where
common
either
theme, yeah.
yeah, and I mean, honestly, out of all of these, I really like the first one you covered, which was the TLS auth bypass. It's just such a feels like a unique situation to end up in where you're able to hijack that TLS connection. Um, like I said, it does require that higher level of access, but it does feel like kind of the most unique of the bunch, where this uninitialized or zero initialized value actually is pretty useful in the context of crypto.
Yeah, I agree. Whenever you have these kinds of state machines where you have to keep track of a lot of information in the state, and just leaving like one thing uninitialized or uncompleted can cause this chain of issues that can be exploited. Um, yeah, it's not like a straightforward, your more straightforward memory corruption type bug like the second one was. So yeah, I'd agree that's probably the most interesting bug that was detailed here. Um, I think the firmware signing issue is probably the most impactful, just because like firmware updating should be something that's fairly easy to get right. Like it should be fairly standard to have some asymmetric crypto or verification on the firmware updates. And because like firmware updates can just be installed with by either chaining with one of the previous bugs or just like with a USB or whatever. And you were kind of mentioning the localized attacker threat model. Um, that's kind of the most egregious bug, I guess, that was detailed here, and also the easiest to understand because it's pretty straightforward. Um, but yeah, an interesting set of issues overall. UPS is kind of an interesting target that I don't think we've really covered before. We've definitely covered IoT and some of the like some of those types of devices, but UPS is just not something I really thought of in terms of targeting. But it
Yeah,
it kind of
not
makes sense, especially when it's such a common product like this one is.
Yeah, I think actually we didn't end up covering it, but just like maybe a couple weeks ago, there was another UPS set of bugs, and I was tempted to cover it. If I recall correctly, the bugs just weren't all that interesting, but the consequence of it, they managed to get code execution on the UPS. And so with that, they were able to potentially overheat the UPS and cause it to, physical damage. So they're also interesting in that sense because they are like this big battery bank essentially, and you can do some damage with that, at least potentially. It kind of
Yeah, there's some
harkens back
physical.
to the old, like, hackers can blow up your computer meme or idea.
Yeah, there's physical and real world implications. So that alone makes it kind of interesting. Yeah. All right, so we'll get into our last topic here, which touches on exploiting a Linux kernel bug that we talked about before on the March 2nd episode for the VOD. Which, for those who didn't see that episode or want a bit of a refresher, was this out of bounds, heap out of bounds write in Netfilter. It required capnet admin, but you could get around that using namespaces. Z covered that in that episode, so you can go ahead and check that out. We have timestamps on the website and such. And I'll let Z get into this here as well.
Yeah, I mean, timestamps on the website, or if you use our Vuln pages, the video, if you click on it, it'll start playing exactly where it needs to. But yeah, covering this one, the bug itself, as a quick refresher, really just had to do with setting up some of the rules for Netfilter that are getting offloaded, or at least in the offload function. In creating the new rule, it would generally, actually, I think they have the code snippet up here. Somewhere in here. Of course, it's somewhere in there, but it would access this entries array, and it would use context num actions, increment it. Um, yeah, here we go. Basically, you've got this one array being accessed by another value. And what I think was, sorry, I'm getting a little bit ahead of myself. But anyway, you've got this access there. Num actions basically never gets validated, so it's able to go out of bounds. Part of the reason for that is the original code has this expectation that there's a relationship here going on, that there's always kind of this immediate followed by the actual uh dup rule or duplicate rule. When you violate that, which you can actually do using the CLI, you have to very manually craft this. If you violate that, then that num actions can actually end up going out of bounds, leading to an access just outside of the actual allocated array. So that was kind of the core issue. What they do call out here is first on the discovery side, they call what actually stood out about this line to them. I think when we were covering it the first time, I just called out, that assumption of um, basically always having the immediate preceding the rule. They call out as something to point out is the fact that this entries array that it's accessing and the num actions, like, basically these structures, this one comes out of this action structure, and the other is just out of the context. These are unrelated. And that's actually a really good point. And something to keep an eye out for is, like, you're accessing an array using something that is apparently completely unrelated. You don't see the connection there. I kind of explained what the connection, or at least the thought process, probably was in writing the code, but you don't necessarily see that connection because these are just two completely different structures. So just something to kind of keep an eye out when you see that. Makes a lot more sense if it's like action entries and num entries or something under actions that is being used to index it. So I think that's a good shout, something I didn't mention the first time we covered this. And a lot of this post is also getting into the actual exploitation of this, at least to the point of a control flow hijack. And so I guess starting off with this is basically this provided them two primitives basically out of bounds right as like the core primitive, and then they had two actual out of bounds rights. One on the ID, one on the dev structure, or net device structure. Sorry, the pointer to the net device. So those happened Kind of focused in on this device pointer, right? Which was 24 bytes past the end of the array. They did a little bit of looking here, kind of figured out, the different allocation sizes so they can land in like, there are no immediates in their rule, then they're going to land in the kmalloc 32. If they have a rule, it's landing in 128, or two rules lands in 192, and so on from there. Walking through a little bit of the memory size here and all of that. Effectively, what it came down to is they can either write at plus 24, like 24 bytes into the next kmalloc 32 or kmalloc 192 slab, or they can write at an 8-byte offset into the next kmalloc 128. So those are kind of like the core primitives that they have, and they basically couldn't find any targets until they were reminded through a Alex Popov's write-up of 4 bytes of power, which I believe we would have covered sometime last year, probably about a year ago.
I'm pretty sure we covered it. Yeah.
Yeah, I mean, I'm quite confident we covered it because I was looking forward to getting that topic, and then he published it. So I'm sure we covered it. I just don't have the date for it. Anyway, he read that kind of inspired him a little bit, and basically just reminded him of one point, is that he could do this multiple times. So yes, he was limited if he basically ran this so the override only happens once, but if he includes multiple dup rules or duplicate rules, it can have this happen multiple times, and kind of keep accessing out of bounds, which kind of a key point, and actually lets him hit some better offsets. So part of the challenge here is finding something of value at the offsets you can actually write to or control. So basically with that, and the Popov post was that he was corrupting on a, I believe it was a message structure, the security pointer, and that was at 40-byte offset, which he could actually hit with this Netfilter bug. That can actually be hit as by doing this multiple times, you could hit like plus 88 or the 88th byte in the kmalloc 128, or 40 of the second next kmalloc 120 slab. So kind of reaching a little bit further out, but being able to hit the right offset in that case. So the actual exploitation here kind of comes down to targeting again that security pointer. Corrupting that security pointer gives a arbitrary freeze. So whatever's in that pointer, that will get freed when the message gets received. So the whole attack here came down spraying the message queue, just these message structures. Fairly common technique on Linux kernel, because these message structures, whatever messages, you have a lot of control over the size that's getting allocated, so you can kind of hit pretty much any slab that you want, or any cache that you want, sorry. And it's with a lot of your controlled data, so very nice when it comes to the exploitation side of things, and common to see used. So sprays that, trying to hit that K128. Yeah, I think it was K128. Frees a few of them, and then adds this netlink rule. Hopefully hitting, kind of getting reallocated into one of the just recently freed message structures. That way it's going to basically be hittable, or be near the other ones, overflow into it. Basically the heap grooming side. Does the out of bounds write 3 times, ends up corrupting the list head previous pointer that's sitting at the 8-byte offset. Message type is sitting around the 88 offset where it writes there, and the security pointer finally of the second. So those first 2 things that I just mentioned getting corrupted, those are sitting in kind of the adjacent memory of like the next message, and then the next one following that is where they're getting the security pointer overwrite. One benefit of using these messages is that you can just kind of message copy out and see which ones actually had their message data corrupted, and that will kind of indicate which which ones are actually corrupted with the security pointer, and just has a way of finding that information out based off the fact that other things got corrupted in them, or um yeah, I mean that's basically just that. Gives them a really powerful way of finding the right thing. I mean, you could have tried to free everything, but because that list head pointer gets corrupted, that's going to break when you free that once, so you definitely don't want to free it. But anyway, using that, he was able to find the corrupted message, to scan for it, and it's getting, if you recall, the primitive here was writing that device structure pointer. That's what's getting written to that security pointer. So he's able to cause a free of that when he receives the message. So basically causes that corruption, frees the message, that frees the net device that's still in use, of course. Allocate more messages using just the message this time, targeting the kmalloc like 4096 or whatever. Hitting that cache, and that's where the net device is sitting. At which point, because a lot of that data is going to be controlled by the message content, has a lot of control there. You can overwrite the ops function pointers, and that's going to give the control flow hijacking. Also worth pointing, because he's able to see the corruptions happening in the message, that will also leak a kernel heap pointer, which can be used for like the KASLR break. So on the whole, go ahead.
More notably, what it could be used for there, and he didn't do this in the exploit, but he makes a note of it at the end. That can be used to bypass SMAP, because for those like that aren't too familiar with SMAP, basically what it means is you can't set up a fake kernel object in user space and point to it, which would be a problem in this exploit scenario, because if you're trying to fake this file operations table, in the way it's done in this exploit, it's faked in user space, which makes it really easy, but as soon as you add SMAP into the mix, you have to then fake that object in kernel space, and you have to know where it is in order to set up that pointer properly. So because you can leak that kernel heap address, and you can get controlled data there, that allows you to fake the object in kernel space, and then you can walk around the SMAP mitigation. So
Yeah,
it's super notable for that.
the other half of that, I was just about to get into that area, is also it can be used more for the for building out a ROP chain in the kernel when you're dealing with SMAP and stuff, where it can't access user line. You've got to build out the whole ROP chain if you want to go further beyond just hijacking control. But where do you point it to? All of that can be done because you have this heap pointer leak into data that you can basically figure out the data that you control and build all of that out of it. So he did not go into the full ROP chain development. Does link to somebody else that did do a more complete exploit. Bond Fee has a more complete exploit for this that includes doing the whole ROP chain. And I've just lost the tab. There we go. But yeah, I mean, fairly straightforward post. I mean, they call it out as being long, but I didn't feel like there was a lot of excess in this post.
No, I don't think there was a lot of fluff. I think it was pretty, like, it was as long as it needed to be. So
Yes, yeah. No, solid post. I mean, give it a read. They go into more details, and I know, especially for those of you listening, like talking about all the offsets and stuff, really easy to get lost in it. But yeah, solid write-off. So I wanted to call that aspect out too. And just kind of an interesting bug. Exploits. I mean, you can see the once you get the arbitrary free. I'm trying to think of how it relates with the 4 bytes power, which also kind of goes that route. Although I think they went with a different structure there. So I mean, there's some things of note in it. So I guess honorable shout out just for the quality of the write off.
yeah, I mean, I must say I love arbitrary free as a primitive. It's just it's just such a cool primitive to have, in my opinion. I might be a bit biased there because one of the first bugs I exploited was a type confusion that yielded arbitrary free, but um, it's just it's a primitive you don't see super often. But yeah, that aside, like this post shows it's really good at going through the strategy of chaining primitives, which I talk about that a lot when we talk about these types of binary topics, but that's because it's such a critical concept. Um, because the initial write that you get with this bug is not really that good. Because, like you mentioned earlier on, you get two out of bounds writes. You get the entry ID, which you basically have almost no control over. It's either going to be 4 or 5, depending on if you use a forward or dup rule. And the dev pointer, which you don't control at all. So, kind of showing how you can take these write primitives that seem pretty limited at first, and then use them to overlap with a different object and cause this sort of type confusion that gives you more powerful primitives. It's just always inspirational to see that. So yeah, I really like this exploit strategy. It doesn't seem to be super stable. I think you mentioned that the stability rate was like 30% success, which is pretty low, but you might be able to get it higher with some additional like heap shaping and whatnot. With things like the kernel, you do have a lot of control over the heap state, or a lot of influence, I should say. So yeah, you might be able to push that higher, but as written, it's a little bit low. But yeah, still really cool exploit strategy, and it does walk around some of those more modern mitigations, like SMAP and SMAP, which unfortunately quite a few write-ups that I've seen in the past, over the last couple years, or let's say 5 years. They just kind of ignore SMAP, or they're like, I just disabled it. Here, he disabled it for the development of the exploit, but you can get around it with that strategy. So yeah, you don't always get to see like the how you can get around SMAP and SMAP. So this post is useful for that too. Gives you some ideas you can try and borrow, just like this post borrowed from Alexander Popov's exploit. So there's definitely stuff that can be taken away and used for other bugs too, which is always nice. All right. Unless you have any last minute things you want to add, Z, I think we'll go ahead and wrap up the show.
No shoutouts this week, so yeah.
All right, cool. So that's all we have for today. Thank you, everyone who tuned in. The VOD will be up on YouTube and Spotify and other platforms tomorrow. Feel free to join our Discord and follow our Twitter for notifications when we go live, or if you want to discuss. Um, we also have the Spot the Vuln channel for any past Spot the Vulns or future ones. It's people try to figure it out and use spoiler tags and stuff. It's kind of fun. But yeah, all that said, we'll be back next Monday and Tuesday for the bounty and binary episodes respectively, and we'll catch you then.